Hi, welcome back. We're in the chapter of the fluids and elasticity now. It is worth mentioning that after we have learned about Newton's laws, back in about chapter 5, 6, and 7, chapter 8 was applications of Newton's laws. There are no new laws to learn this semester. Everything, the rest is an application of it or a different form in a different mathematical way of looking at it, such as conservation of energy and momentum. Rotational motion was also an application of Newton's laws. And today we're going to apply Newton's laws to fluids. And so what is a fluid? Simply put, as the book puts it, a fluid is a substance that can flow, and it can be also thought of, or as a consequence to that, since it flows, it cannot maintain its own shape, and so it takes the shape of the container. There are two kinds of fluids that we will talk about, the gases and then the liquids. We will focus mostly on the liquids, but we'll also talk about the gases. So, as you may imagine, gases, the gas molecules, are farther apart than the liquid molecules, and so they have even more freedom to move. So gases, in gas molecules, the molecules are free to move in space, and the molecules do not interact except for occasional collisions with each other or with the walls of the container in which you put them. And the gas molecules are far apart from each other, and so the gas is easily compressible. We can change its, shrink its volume by applying pressure, by applying a force to it. I haven't talked about pressure yet, so I'm avoiding that word. Liquids, on the other hand, the molecules are weakly bound and stay close together. A liquid is incompressible, to a really good degree. So basically, we can think of it as you cannot change its volume by applying a pressure to it. And so the molecules cannot get any closer to each other. And then there are weak bonds between the molecules to allow them to kind of move around locally, right? So with solids, for example, the molecules are, let me just draw a solid. Solid, the molecules are kind of organized with each, they are organized. So this is a solid here. Kind of stay there. They can vibrate up and down, left and right, but this molecule, you will not find it there, and this molecule does not move here. So they stay local, very local. With liquids, the molecules can move apart, but just locally. For solid, we say it has long-range order. For liquids, they have maybe short-range order, but not long-range order. So this molecule can be moved there. You can easily, for example, for water, by just shaking it, you can just take molecules from one part to another. So this is solid, liquid. For gas, the molecules are just far apart from each other, and they are just free to move. They are free to move around. Okay. Now, volume and density. The volume is of a substance or an object is how much of space does it occupy, and the SI units for volume are cubic meters. And there are ways to calculate the volume, right? If you have a cube, it's the length cubed. If it's a box, it's length times width times height. If it's a cylinder, then it's the pi r squared times the height of the cylinder. If it's a sphere, it's 4/3 pi r cubed. Anyways, there are formulas to calculate volumes for regular objects. So if you know the volume of the object, you know its mass. The mass divided by volume will give you the density. Density has the symbol rho, and the units for density are mass over volume. So the dimensions are mass over volume, and so it's SI units would be kilograms per cubic meters. Okay, kilograms per cubic meters. Gases, because the molecules are farther apart, they have very low density. So, for example, the density for air I think it's like 1.29 kilograms per cubic meter, and it depends on the temperature really strongly. So the density becomes lower if you apply temperature, the gas expands if you increase the temperature. Liquids and solids, their density is fairly constant. For example, the density of water is in kilograms per cubic meters, it's 1,000 kilograms per cubic meters. As you see, it's much larger, about 1,000 times. And liquid like mercury Hg, is, I believe it's 13,600 kilograms per cubic meter. Anyways, the concept is fairly simple, mass per unit of volume. I can read you a few from my chart here. So for example, helium gas has a density of 0.18 kilograms per cubic meters. Air, as I wrote, 1.29. Gasoline, which is a liquid, will be 680 kilograms per cubic meter. Oil, like typical oil, would be about 900 kilograms per cubic meter. Water is 1,000. And I will just read the numbers. Seawater, about 1,030, more dense than water. And then mercury is 13,600, as I wrote over there. Now, the concept of pressure. When we talk about an object, like a solid object, it makes sense, or a set of objects makes sense to talk about the force, but for liquids and or for fluids in general, it makes sense to talk about pressure, because you're not dealing with one single object, you're dealing with a collection of a lot of molecules. So it makes sense to average things. So it would be the force per unit of area. So how do you apply pressure to an object? So let's talk about the concept of pressure and then how it arises. So let me see here. So for example, let's say I have I push on this board. I can apply a force. Let's say I can apply a force of 1 Newton, and I'm free to apply the force. I can apply a force of 1 Newton by using the tip of my finger or using my palm here, the palm of my hand, applying 1 Newton. But here, 1 Newton is spread over a little area, whereas here it's 1 Newton but spread over a larger area. And so the pressure, when you spread the force over a tiny area, pressure divided by a tiny area, you get force divided by a tiny area, you get a large pressure. On the other hand, if you spread the force over a large area, then you will get a small pressure. For example, if you want to pop a balloon, if you push on it with your index finger or your thumb, usually you can't pop it unless you apply a really, really large force. On the other hand, with a small needle, you just poke it and it explodes. The reason is because a needle has about 10,000 times less area than your fingertip, or maybe, about 10,000 times or so less area than your fingertip. So if you divide 1 Newton divided by an area that's 10,000 times less, gives you a pressure of 10,000 times more. So you just focus that force into one little area. And then on the other hand, also you should notice that, so let's say this is this is an area here, you can think, so here is the object. If I want, I'm looking at, here's the object coming out here. I have to apply it, well actually let me talk about the board itself. If I want to apply a force on it, if I apply a force parallel to the board, that doesn't cause pressure. Only the part of the force that's perpendicular is the part that causes pressure. And so this part here is understood. This is the perpendicular part of the force. So if I take an object and I apply a force this way, only this part of this force will have two parts, right? One of them is parallel and the other one is perpendicular. This is the perpendicular part, and that's the one F perpendicular, and this one is F parallel. The pressure will be this force divided by the area. That'll be that. Okay. Let's dig a little deeper into pressure. Pressure here. well erased. Okay, now it is. So let's continue pressure. Imagine you go to outer space where there is no gravity. You take a liquid, let's say mercury, right? Mercury, because it kind of holds itself. And you place mercury into a container, and the mercury just floats. I mean, it doesn't fall because it's in outer space. Everything is falling at the same rate, so it just stays there, floats. So the question is, what is the pressure inside this container? Imagine I suck all the air. The only thing that's contained in this container is the mercury. Well, the pressure inside the container would be zero. The reason for that is because to apply pressure, somebody has to be pushing on the walls of this container. Somebody has to hit it. And there is nothing that collides with it, so we conclude that the pressure here, assuming it's complete vacuum, will be zero. There is no pressure. That's if you have a mercury here and it's a liquid. On the other hand, if I have a gas, the gas molecules, even in outer space, right? The gas molecules will be moving. Will be moving in some random directions. You will learn about this when you do thermodynamics in the next course. And there is the kinetic energy of these defines a temperature. And so, as long as the temperature here is not absolute zero, these are, at least in the classical picture, they're moving. Okay, so they would be moving and hitting the container, hitting the walls of the container, and so there would be pressure. There would be pressure here. Even in outer space, where there is no gravity, these would still move. These are moving, vibrating just locally, but the mercury molecules, you don't have a mercury molecule splitting up and coming here. I mean, very few. Okay, this is in outer space. However, bring this experiment to Earth. So bring it, this is in outer space. Let's come to Earth. Come to Earth, what happens to this mercury drop? Well, that mercury drop, it will fall down and fill out this part of the container. And now there will be pressure here. This is still vacuum. There is no pressure here, but there will be pressure here. Why? Because the weight of this, it's being pulled down with an mg, that's a force, and so the wall will apply a force back of a normal force on the fluid. So by Newton's third law, the fluid will apply a force back on the wall. Basically, it is equal to mg, and it is just however much the weight is, and then you divide it by the area, and that will give you a pressure. But let's not worry about quantitatively yet. But you can see that this will apply a pressure. The same thing here for the gas. The gas molecules, because of gravity, they will still move here, but because of gravity a little bit, it will affect them, and so the collisions, they will hit more toward the bottom than on the top, and so there will be a little more pressure on the bottom than on the top. So you conclude that the pressure will have two components. One of them is due to gravity, and the other one will be due to just the thermodynamics here, or the kinetic motion of the gas, the thermal motion of the gas. So there are basically two origins. You have the gravity, just gravity pulling it down, and therefore it will, the fluid will push against the container. And the other one will be the thermal. As you can see in the outer space, basically the thermal took over completely. On Earth, for a fluid, it is mostly it is the gravitation that causes the pressure, the gravity. For a gas, it is still the thermal. Like in a lab container that is this size, gravity will have very little contribution, like less than, I think, 1% or so to the pressure. It's mostly thermal. However, if you take a column of air, so here is Earth, and you go really up on the atmosphere, you will find that there is more air here than here. Here there are fewer air molecules than here. Okay, so the pressure on Earth is more at the bottom than at the top. In fact, it will decrease the pressure will decrease as you go to the top. It will decrease. Okay, the pressure will decrease because basically the air, there is less of it here than here. Now, once you're in let's say you take a container of water, let's say. Let's take a container. There's a container. It's filled with water. And we will see that the deeper you go, the more pressure there is, because think of it like think of somebody standing on your chest. If you go deeper here, if you go here, there is only this much water on top of you. If you go here, there is even more water on top of you. If you go all the way to the bottom, there is basically all of this column of water right on top of you. And so there is more pressure as you go deeper. And it basically ends up being, it will increase linearly with depth. And one way you can think of the pressure is, take a spring, here is an apparatus, and close it like this, and it has a spring here. There is a piston here, and this piston can move down and it can move up, because there is a spring here. So if I place a weight here on it, the container will compress, right? The container will drop, and it will, so this is without the weight. If I place a weight on it, it might compress to this much if I place a weight. Now, to figure the pressure, you can find, because you know the area, and if you compress the spring, it will compress by an amount x, and the force is kx, so that's the force from the spring, and it has to equal to the force coming down, and the force per unit of area will give you the pressure. You bring the spring here. If you put, let's say you come here at a particular spot, it doesn't matter whether you put the spring vertical, whether you put it this way, or whether you put your apparatus, sorry for my drawing, trying to draw small but yet big so that you can see it on the camera. It does not matter. It will compress by the same amount. So the pressure at a particular point will be the same. Liquid is pushing you this way, it's pushing you this way, it's pushing you this way, it's pushing you this way. You're being pushed this way, you're being pushed this way. In every direction, the pressure will be the same because there are forces. And at that one point. The same thing for air in the atmosphere here. There is air on top of us, right? Imagine I'm standing here, and I'm right here on Earth. I'm not this tall, but there is Earth, and there is a whole column of air on top of me. If I spread my hand, there is air coming down, hitting my hands like this, and there is air hitting my hands from the bottom. And so there is pressure from the top, and there is pressure from the bottom. And we will see that there is something called atmospheric pressure due to the atmosphere itself. And it has a value of, by the way, I have pressure is force over area. It's newtons per square meter. Force over area, newtons per square meter. And it's called the Pascal, Newton per square meter. You will hear both Pascal or Newton per square meter. And the pressure due to the atmosphere, atmospheric pressure, is 1.01 times 10 to the 5th newtons per square meter. Newtons per square meter. And so, for example, if I want to calculate the pressure of the atmosphere on my hand, let's say, is 15 centimeters by about 4 inches, about 10 centimeters. So 15 by 10 centimeters, so the area is 15 centimeters, that's 0.15. By 10 centimeters, that's 0.1 meters. And so this is 0.015 square meters. That's 1.5 times 10 to the minus 2 square meters. And so what's the force on my hand? Well, we know that pressure is force over area, so the force is pressure times the area. And so you get 1.01 times 10 to the 5th times 1.5. 1.01 times 1.5 is approximately 1.5, and then 10 to the 5th times 10 to the minus 2 is 10 to the 3. So this is about 1,500 newtons. It's like I'm holding 150 kilograms on my hand. That's about 350 pounds down this way. So why am I not getting tired? The reason is because there is 1,500 newtons from the top, but there are also 1,500 newtons from the bottom, so my hand stays balanced without effort. So yeah, I mean, the thickness of my palm is irrelevant here, because the variation of pressure from this point and this point will be the same. The depth is not appreciable. Okay, so that's atmospheric pressure, and it amounts to a lot, actually. And that's how suction works, like those suction cups, that's how they work. For example, let's say I have a, let me erase here, just to show you a suction cup. Take one of those suction cups, they're kind of round, and you push it against the wall so it's completely empty from air. So here is a wall, and here is the suction cup. This is the suction cup, and if you look at it from the top, it will look like this. So it looks like this, and here is the wall. That's the suction cup. And then you hang something from it here, a mass, let's say M, a mass M, and you ask how much mass can it hold. So if it's completely empty, the suction cup, from inside there is no air. So think of it, so here's my hand, here's the suction cup, let's say it's here. What are the forces on it? Well, the forces on it are, you got the atmospheric pressure this way. You got the atmospheric pressure this way, and then there is, so let's take this whole thing. There is the atmospheric pressure, and then there is the mass times gravity. The suction cup basically doesn't have much mass, so it's only this. So that's the mg. So there is the force of the atmospheric pressure, force from the atmospheric pressure, minus mg, and if it's hanging in there, that would be 0. So I want to know basically how much mass can I hang before it falls down. The force from the atmospheric pressure would be the atmospheric pressure times the area equal to mg. Now what's the area of a suction cup? Well, let's say it is radius 10 centimeters, and so the area would be pi r squared, and it is pi times 0.1 to the power 2, and that's 0.0314 square meters, 0.0314 square meters, that's the area, or 3.14 times 10 to the minus 2. Yeah, I should leave it like this. 3.14 times 10 to the minus 2. And so the mass, therefore, would be the pressure times the area divided by gravity. The pressure is atmospheric, so it's 1.01. 1.01 times 10 to the 5th times the area, which is 3.14 times 10 to the minus 2, divided by gravity, which is about 9.8. And so 10 to the 5th times 10 to the minus 2 is 10 to the 3rd. Gravity is about 10, so 10 to the 3rd divided by 10 is 10 to the 2. And then 1.01 times 3.14 is about 3.2 or so. Let's say 3.2. And so, so that's 320 kilograms. So you can hold about 320 kilograms with a suction cup. Okay, that's a hefty weight, but usually suction cups don't hold that much. 320 kilograms, you're talking about like 600 or 700 pounds. They don't hold that much because you can never get them to be completely vacuum inside. But nevertheless, they do hold a good amount of weight. All right, so the next step, I would like to talk about the variation of pressure with depth. How does pressure vary with depth in a fluid? All right, so I will do that in the next video.